So I hope you can see the slides. Anders, can you see them?
Yeah, I can see them, yeah.
Excellent, thanks. So the first slide is called small charges of natural refrigerant. And the cause for that is me and Claes Andersson started a few weeks ago doing a presentation on this topic. And we had 4 points in this presentation, but both me and Claes were a bit too keen to talk about our topics. So the time ran out and we had to skip the last part. And the last part was then EcoPack, which I'm gonna continue talking about today. If you're interested in the other topics that were presented last time, there is a link in the chat where you can find a YouTube session of it. The link is also down here. So that was about that. So the prerequisite, when should we use EcoPack or a solution like EcoPack? What we are aiming for is to build a heat pump for domestic heating and tap water heating. So that means we will have a condensation temperature around 40 to 70 degrees somewhere. In this project, we are looking on a smaller application, meaning private houses or bigger flats, so somewhere in the range of 5 to 10 kilowatt. And we are aiming to be able to install these heat pumps indoors, and that makes a kind of frame for it. The maximum allowed charge, since we're dealing with flammable refrigerant, is 150 grams. Preferably, we would like to have a low noise, so we don't disturb the people living in the flats. And of course, since housing in flats is really expensive, we like a small footprint. What is different on this type of machine from a normal ground source heat pump or an air heat pump is that we're aiming to connect this to something that is a bit warmer than the ground. So we're looking to connect it to something that is around 15 to 40 degrees. And that could then be a thermal grid or a thermal energy storage, and most likely a borehole thermal energy storage. The heat sources for this can then be grocery stores, office building, or ice rink, where today we normally use a gas cooler to get rid of the excess heat. But instead we can then take this low-grade heat that is around 40-50 degrees and feed it into a thermal grid. This heat source could also be solar thermal, where we in the summertime then heat ground in a B-test and then use it during the winter. What we also see is there is a lot of talk that there is a too low electricity in the few hours in the winter, but a bigger problem in the future will probably be that we will have too much electricity and too low transmission possibilities, meaning that we somehow have to get rid of the surplus of electricity. And one way of doing this is, of course, running heat pumps and then feeding the heat into the ground. A special application where EcoPack also can be used is as an economizer for a larger heat pump. And what is this then? For this application, we're then talking about the same temperature ranges and the same design. And the positive sides that we're aiming for is reduce losses, increase COP, and increase power. So what is an economizer? Let's say we have a larger big heat pump that on the cold side is connected to the ground and on the warm side is connected to a large building. Then one of the major losses in this system is the throttle losses in the expansion valve. And one way to decrease these or reduce them is to connect another heat pump or an EcoPack so that we subcool the liquid even more than it's subcooled after the condenser. so that it's more subcooled before it enters the expansion valve. If we look on the sizes here, if we have a Z value, and a Z value in our case is then the dimension of the two systems. So if the EcoPack is 1/4 of the larger heat pump, and we assume a temperature for the larger heat pump running at 50 degrees condensation temperature and -7 degrees evaporation temperature. And we also have the two refrigerants, propane in the larger one and isobutane in the smaller one. We expect that the outcome will be a 14% increase in COP and that the cooling power will increase 26%. And that the cooling power will increase is, you can see it's correlated to the Z value pretty well. So who are we that are doing this project? We have Professor Björn Palm from KTH, and together with him we have had 2 master theses, Elsa Forsgren that was working with us last fall, and at the moment we have Kristoffer Kronström working at KTH doing his master thesis. We have Professor Emeritus Erik Granryd, who has been in this field a long time and been active with decreasing charge filling. We have Claes Andersson, who is really driving this kind of project, but also the whole idea to decrease the charge fillings. Jan-Erik Novotny, he has been leading Elsa and Kristoffer in their master thesis, but he has also been in this business for a long time. If I understand it correct, he was one of the first people that drilled a borehole in his garden to use a ground source heat pump to heat his house. And then it's me working at the Swedish Heat Pump and Refrigeration Association, and that trying to keep the project together. Together with us, we have some really great companies. We have Sanden, who is delivering a compressor that normally is used in the automotive industry. We have Alfa Laval delivering heat exchangers. We have Kylma that is delivering both heat exchangers and compressors and other bits and pieces so we can build a system. And then we have 2 customers or producers in the system. We have Megawatt Solution that is looking on using the EcoPack solution as an economizer. And then we have Nibe, as most of you probably know, a really big heat pump producer. And the Energy Agency is helping us funding this. The budget for the whole project is 150,000 euros. So it's a very low budget, I would say. But with the help of dedicated people and dedicated companies, I think we have come a really long way in this project. So what is the spec for the EcoPack? So far we are using 120 gram of isobutane or R600A. Condenser and evaporator is submitted from Alfa Laval, and these are then asymmetric heat exchanger, so that we can have this really low charge and still have a good heat transfer. We have the compressor from Sanden that normally is used in the automotive industry. It's a scroll compressor and it sounds a bit like a sewing machine. And it has, besides being really low noise, it has the benefit that it doesn't take much charge. So it's a nice compressor to work with if you want to reduce the charges. So far we're using standard ester oil, so nothing special about the oil. So all these components are industrial and can be found on the market today. What we still are struggling with, or that needs a bit of work, is the internal heat exchanger that we're using. Here we're using a custom made or a handmade. expansion heat exchanger, and electronic expansion valve is a industry standard expansion valve, and it's working great, but we do have a few problems. One of the problems is that the compressor is able to run over such a large range, meaning that we can't really use one expansion valve to control the whole range. The other problem we have with the expansion valve is that today we are measuring the superheat after the evaporator, but after the gas has run through the internal heat exchanger, we get an even higher superheat. And this would be fine if we only have one working point, but since we are running the system in such a different position and such a different revolutions on the compressor, we get really different superheat coming into the compressor, which is not so beneficial for the whole COP of the system. So one idea is to move the expansion valve sensor right before the compressor. All experts we are talking with are saying that this is impossible, but we might try it in the future. And another idea we have is to don't measure the superheat, but actually measure the subcooling after the condenser and control the system this way. So this is a bit of work we still have to do, but I think that's a different project in the future. Maybe I should say a few words about the system. As you can see, it's a normal heat pump with the extra heat exchanger before the compressor, after the condenser, the internal heat exchanger. And the reason that we have this is that we use the natural refrigerant isobutane, and we want to make sure that the superheat is high enough so we don't have any oil solved in the refrigerant, and that we also gain a bit of efficiency by adding that part. I should also say, if you're interested in the different parts and the different design of this, you should really listen to the presentation that Claes did that we'll link to. So how is this working then? If we are running the machine on 2000 revolution per minute, and then I should explain what the different things here. On the x-axis, we then have the evaporation temperature. So we are measuring here 15, 25, and 35 degrees. And on the different colors are different condensation temperatures. So it's 50, 60, and 70. And the denotation M is measured values and E is estimated or theoretical values. So we can see that the theoretical value match pretty well the measured values, and the output that we then get in power of heat is between 2 up to 3, 4, something like that, when we run the compressor at 2000 RPM. If we speed up the compressor a bit to 6000, then we'll have an output between 7 and 11, something like that. And then I should say that this was done between 2 and 6000 RPM. The compressor itself is actually able to run between 800 and 8500. So there is a very, very large range that is possible to run in. But this also puts a lot of pressure on all components, and especially the expansion valve. Yes. So how well is this working then? The COP of the system, when we run it at 4000, you can see that when we have 15 degrees evaporation temperature, we have a COP between 4 and 6, something like that. And if we increase the evaporation temperature, we will then have a COP all the way up to 9. And this is, of course, the reason why we want to go in this direction and heat up the cold side of the system, because normally we see COP values maybe between 3 and 4 in normal heat pump, but here we then double it. So it's really nice to see, and it's also really nice to see that the theoretical values match the measured values really well, besides the really high point of 35 degrees evaporation temperature. And I think this could be due to excess superheat, but it could also be due to measuring problems in the rig. So, but how is this then compared to a standard component using normal heat exchanger, a normal top of the line compressor? So to find this out, we build a similar rig that we run in parallel, and here we bought a Bitzer compressor, 4-stroke semi-hermetic, and used the oil that they recommended, which is then a PAG oil. We bought normal heat exchanger from Svep, and these were, of course, they are not asymmetrical, so we needed a bit more of refrigerant to make the system work. So we ended up with around 1 kilo, a little bit less. We used the same expansion valve. As you can see in the output, the power output, this machine is almost 3 times as big as the other machine we showed. And the reason for this, that we build it a bit bigger, is that it should fit Megawatt Solutions machines, so they could integrate this in their system later on. So if we look on the comparison here, if we start with a diagram to the right, we then have condensation temperature of 55, 60, and 70 degrees. And if we only look on the one that is 70 degrees, we have measurements similar in the standard component rig. And then we look where we are between 26, 28 degrees. We have marked it round. And what we can see is then that the COP, or the coefficient of performance, is actually the same for the both system, more or less. And then you can say this was kind of dull. Didn't we make something new, something better? But if we look on the charge filling, for the standard component, we then used around 40 gram per kilowatt when we had a temperature different at 43 degrees. And if we look on the new system, we only use 13 grams per kilowatt at the same temperature difference. So I think here we have really proven that it is possible to build systems that use a lot less refrigerant and still match the same performance, which is actually what we was hoping for. So with this, I would like to say many thanks. If you are interested, we have a web page where you can find this, varmtokallt.se. Last time I spoke a lot about refrigerant, and I would like to highlight, if you go to köldmedier, Swedish for refrigerant, then you can find a lot of publication concerning this. So with this, I would like to say many thanks once again. And if you have any questions, don't be shy to present them.
Victor, we got one question here from Jan-Erik Novaki. Blitzen is, of course, a 4-cylinder machine, not 4-stroke.
Okay, thanks, Jan-Erik.
Any more questions? Or someone who wants to raise their hand?
It's perfectly fine to ask the question in Swedish, that is easier.
Vi är säkra på att det gav några tankar i alla fall. Så att, välkomna att ställa en fråga så.
Let's see.
You see the question yourself.
Yeah.
How do you regulate the superheat, manually or with the help of a controller?
Both, I would say. We're trying to use a PID controller, but we need to change the values a bit for every set point. So we're trying to use the controller and the PID regulation, but it's not that easy. So it need a bit of hand job on it. I could add to that, one of the really big problems we have is to measure the correct temperature, because if you measure the temperature outside the tubes, which are then extremely short in this case, we are more measuring the temperature of the components next to the tube. If we place it between the internal heat exchanger and the evaporator, for instance, we're not measuring the temperature of the superheated gas, but we're more measuring the temperature of the components between. So that is something that we need to work with and get the measurement into the system.
Yeah. And ni är naturligtvis välkomna, or you're of course welcome to come with questions later on to us if you don't have them now. Jonathan asked another question. Why R600A or not, and not R290?
The reason is that the evaporation temperature are quite high, so we don't really need the high pressures that we get from R290. And R600A is a really good refrigerant for this temperature range. Another reason is, of course, also that this is a experimental research project, and a lot of work has been done so far with propane. So it's also beneficial to use isobutane in that case. For instance, when we discuss what kind of oil we should use, it was really hard to find any background or any guidance on that. So I think it's beneficial to do work on something new that also can contribute.
Jan-Erik asked another question here. Could district heating return temperature by used as heat source?
Yes, for sure. That is one of the applications that we're also looking on. If you have a district heating net and far off where you don't have the enough high temperature, then you can also add this type of machine, and then you can still use the fairly low temperature and raise it to the wanted temperatures.
Yeah. It looks like we're running out of questions here. We would like to thank Victor for a great presentation, and thanks for listening and participate, I would say. Or do you want to add some famous last words, Victor?
No, thanks for listening. Take care, everybody.